When you hear about cyber attacks, what's the first thing that pops into your head?
Usually things like data breaches, right? Or maybe ransomware hitting a company.
Yeah, exactly. Or, hacktivists defacing a website. It's almost always about digital disruption, isn't it? Messing with information online.
That's the standard picture, and yeah, for a long time, that was pretty much the story. Attacks hit IT systems, your databases, email, corporate networks.
The damage stayed digital, even if it cost businesses money.
But there's this other category of attack, one that feels, well, frankly, a lot more unsettling.
You mean attacks that jump from the digital world into our physical world?
Precisely. We're talking cyber attacks that actually cause real-world physical harm. Things like disrupting essential services, wrecking expensive equipment, maybe even creating dangerous situations.
For years, that really did sound like something out of a movie, like science fiction.
It absolutely did. The idea of sending some code and making, a generator explode or a power grid collapse, it seemed like there were too many barriers, too much specialized tech in the way.
Well, that barrier, it's been broken. And that's what this deep dive is all about. We're getting into the world of cyber physical attacks targeting operational technology, or OT.
Right, OT. Not the IT systems managing data, but the systems that actually interact with the physical world.
The controllers, the machinery, the processes.
Yeah.
The stuff that keeps modern life running. Factories, pipelines, transport.
And critically, power grids, water treatment plants. These are run by OT systems, sensors, actuators, the software making physical things happen.
So manipulating those systems from the cyber side, that's the goal of a cyber physical attack.
That's it in a nutshell.
And our guide for understanding this today is a really excellent executive research report. It's from Honeywell's Global Analysis, Research, and Defense Team, JRD, they call it. The report's called the Cyber Physical 6, and it's very focused, looking at a really specific group of incidents.
It is. It digs into the history and, importantly, the trends across what were, when they wrote it, the only 6 known examples of malware or attack campaigns built specifically to cause physical impact using cyber means.
Only 6? That seems like a small number.
It is small, which makes it a unique data set. But looking at them together is incredibly revealing about how these threats work and how they're evolving.
The Cyber Physical 6. Okay, so our mission here is to really get to grips with these 6 attacks, understand what makes each one significant.
Yeah, and identify the key trends that the Honeywell GRD team pulled out from looking at them collectively.
We'll look at the methods attackers use to get physical effects, and crucially, discuss what we can learn and maybe what to expect next.
The aim is to give you a clear, solid understanding of this critical threat area, helping you grasp the reality and the stakes involved with cyber-physical risk.
And before we dive into the 6, there's one name that always comes up first, the one that proved this wasn't just theory anymore.
Stuxnet. Have to be Stuxnet. Discovered back in 2010.
A real watershed moment, wasn't it?
Absolutely. It was the first confirmed real-world case of malware specifically built to cause physical destruction by hitting industrial control systems. Before Stuxnet, honestly, a lot of folks in security thought it was either impossible or just way too complex to actually pull off. Stuxnet shattered that idea.
Okay, so let's start the story there with Stuxnet, the first of the cyber physical 6.
Right. And the Honeywell report frames these 6 as unique. As you said, there have been tons of cyber attacks hitting industrial systems for spying, stealing data, causing disruptions, maybe.
But these 6 were different.
Yeah, the report singles them out for their explicit design to cause physical effects. And wisely, I think, the report doesn't try to rehash every tiny technical detail of each attack.
Right.
Others have done that extensively.
Sure, Stuxnet's been analyzed to death.
Exactly. The value here is looking at them as a group to see those bigger patterns, the trends, the lessons learned.
So Stuxnet, 2010, just how big a deal was it?
Oh, it was huge. Not just the first, but incredibly sophisticated for its time. The report highlights some key things. Its massive code base, apparently bigger than many operating systems back then.
Really? Wow.
Yeah, and its use of multiple zero-day vulnerabilities.
Which are flaws nobody knew about, right? Unpatched.
Exactly. That gave it a huge advantage. Plus, it had this remarkable ability to spread really widely, but at the same time, it was laser-focused, searching for a very, very specific target configuration.
So it spread like crazy, but was only looking for one particular setup.
That's the idea. Yeah. It was hunting for specific Siemens, somatic PLCs, programmable logic controllers, and only those controlling frequency converter drives connected to centrifuges. And even then, only if they were set up in a very specific way.
And when it found its target.
Then it switched to its attack phase. And the goal wasn't just disruption, it was physical destruction.
Right, it actually broke things.
It did. Stuxnet messed with the physical operation of those centrifuges. It used the industrial protocol, Profibus in many cases, to talk to those Siemens PLCs. And it subtly changed the commands going to the frequency drives, making the centrifuges spin too fast or too slow outside their safe limits for periods of time.
Causing stress and vibration.
Exactly, which ultimately led to physical failure, breaking the centrifuges. That direct physical damage was the game changer, a first for malware.
The report mentions Stuxnet being unguided. What does that mean in practice?
It means that once it got onto the right system and was configured, it could pretty much run on its own. It didn't need constant live instructions from the attackers, what we call command and control, or C2 for the actual attack part.
So the destructive logic was built in.
Yeah, the logic to find the target and then execute the manipulation sequence was embedded right there in the malware.
That sounds powerful, but the report also calls it noisy. Why noisy?
Well, because its strategy was to spread far and wide to find that needle in a haystack. It used things like infected USB drives as an initial vector.
Ah, the famous USB connection.
Right, so it ended up infecting a huge number of systems all over the world. The report cites figures like over 100,000 in a year across many countries.
Which made it easier to spot.
Exactly. That widespread infection made it much more likely that security researchers would find it, pick it apart, and figure out what it was doing, which of course they did.
Okay, so Stuxnet. Super complex, very targeted, physically destructive, autonomous for the attack phase, but noisy because it spread so widely using USBs and hitting protocols like Profibus. What happened next? Did the floodgates open?
Not immediately. There was actually a gap, about 5 years according to the report's timeline. The next big known incident with physical impact came in 2015. That was BlackEnergy.
BlackEnergy. Targeting Ukraine's power grid, right? Caused major blackouts.
That's the one. Significant, prolonged power outages.
So how did BlackEnergy stack up against Stuxnet? Was it another piece of super complex malware?
Actually, no. And that's a key difference the Honeywell report points out. BlackEnergy wasn't really about incredibly sophisticated zero-day filled malware like Stuxnet.
Okay. So how did they cause the blackouts then?
It was more about a highly coordinated campaign. They basically misused legitimate access and existing system capabilities.
Misused what was already there.
Yeah. The attackers got into the network, obtained valid user credentials, and then used remote access tools, the same kind administrators might use to log into operator workstations. From there, they interacted with the human-machine interfaces, the HMIs.
The screens the operators use to control things.
Exactly. They used the HMIs to manually click buttons and disable circuit breakers at multiple electricity substations, pretty much all at the same time.
Wow. So less about exploiting a technical flaw, more about hijacking the normal controls through stolen access.
That's a good way to put it. It was strategic, coordinated misuse across many targets simultaneously. And they didn't stop there.
Oh, what else?
The campaign included other elements to, maximize the chaos and make recovery harder. They deployed destructive malware wipers on some control system servers to trash them.
Crippling the systems.
Right. They also scheduled disconnections of the backup power supplies, the UPS units, at operator sites. And they even launched denial-of-service attacks against phone lines and communication links to stop the power companies from coordinating their response effectively.
That's thorough.
It was a multifaceted campaign. The actual remote access malware involved was a variant known as BlackEnergy 3, which is why the whole incident often gets called BlackEnergy.
Got it. So BlackEnergy expanded the playbook, showed that you didn't necessarily need Stuxnet-level malware. Coordinated misuse of legitimate access could also cause widespread physical disruption. What came next in this cyber-physical sequence?
Well, things seemed to pick up pace then. The very next year, 2016, brought another major attack, and again, it hit the Ukrainian energy sector. This was Industroyer.
Industroyer. Okay, how did that one evolve the game?
The report describes Industroyer as another significant step up. It wasn't just a single piece of malware. It was designed as a configurable, modular framework.
A framework, like the toolkit for building attacks.
Exactly like a toolkit. It was built with different components, or modules. The report specifically mentions 4 distinct modules it contained.
What did these modules do?
Each one was designed to speak a different industrial protocol. You know, the specialized languages that devices out in the field, like circuit breakers or protective relays, use to communicate and receive commands.
Ah, so it could talk directly to the equipment.
That's the key. Industroyer had modules for IEC 608780, 5101, IEC 70870-5104, IEC 61850, and also OPCDA, that's OLE, for Process Control Data Access. Common languages in the power industry.
So unlike BlackEnergy, which had to go through the operator screen, the HMI.
Right, using stolen accounts.
Industroyer could bypass that layer entirely. It could just send commands straight to the devices using their own language.
That's the critical difference the report highlights. By implementing these protocols itself, Industroyer could be placed on a system inside the OT network and then issue commands directly. No need for compromised user accounts, no need to interact with the graphical HMI. Direct control.
That sounds much more, well, powerful and potentially stealthier.
It can be. But the report notes an important dependency for the original Industroyer. It needed active C2 communication.
Command and control again. Why?
It needed to connect back to the attackers to get its instructions. Basically, to be told which protocol module to activate and what specific commands to send to which specific target devices. The payloads were configurable and delivered via C2.
Got it. So Industroyer, modular framework, direct protocol control, but needs to phone home for instructions. What followed that?
Next up in 2017 was Trisis, also known sometimes as Triton, and Trisis. Trisis was groundbreaking in a really alarming way.
How so?
It was the first known malware specifically designed to target safety instrumented systems, SISS.
Safety systems. You mean the emergency shutdown systems, the absolute last line of defense.
Those exact systems. And the Honeywell report really emphasizes the terrifying implication here. SIS are purpose-built, highly reliable systems designed only to detect dangerous conditions. Think extreme pressure, temperature, vibration, and automatically trigger corrective actions, usually a safe shutdown, to prevent accidents, explosions, fires, catastrophe.
So targeting the SIS, that's like cutting the brakes before you crash the car.
That's a perfect analogy. If an attacker can disable or manipulate the safety system, they remove the one thing designed to stop their other manipulations from causing maximum physical damage. It potentially allows the full impact of their primary attack to happen.
That's chilling. Was the Trisis malware itself super complex, like Stuxnet?
Interestingly, the report notes the malware structure was relatively simple. It was basically a compiled Python script that contained or dropped some other executables.
So the sophistication wasn't in the code itself?
Not primarily. It was in the target and the implications of hitting that target. The method was also different.
How did Trisis attack the SIS?
It communicated directly with specific models of SIS controllers, the brains of the safety system, and its goal was to replace their legitimate, safety-certified programming logic with malicious logic crafted by the attacker.
So it reprogrammed the safety controller.
Exactly. Instead of doing its safety job, the controller would now run the attacker's code. That could mean ignoring real danger signals or maybe even actively triggering unsafe conditions itself.
What did the attackers need to pull that off? It sounds like you'd need to know a lot about the specific target.
Absolutely. The report makes it clear that while the malware code might seem simple, the overall attack required significant effort and intelligence gathering beforehand. Attackers needed a deep understanding of the specific SIS hardware, its configuration, its logic. They also needed to establish a solid foothold inside the industrial network, likely bypassing several layers of security, and maintain reliable C2 communication to deliver that very specific, customized malicious logic payload for that particular SIS.
And run it from somewhere that could actually talk to the SIS controller.
Yes. Critically, it had to run from a machine that had network connectivity to the target SIS controller, which are often, or should be, heavily isolated for security. So the impact here wasn't from manipulating a standard protocol like Industroyer did. It was from changing the fundamental program logic running on the safety device itself.
Okay, so we have Stuxnet, complex, destructive, BlackEnergy, coordinated misuse, Industroyer, protocol framework, C2 needed, and Trisis, targeting safety logic, needs deep intel and C2. That takes us to 2017. Was there another gap then?
Yes, a few years went by without major new public revelations in this specific cyber-physical category. Then, bam, April 2022 hits, and we get news of not one but two significant new threats. Industroyer 2 and Incontroller.
Industroyer 2, a follow-up to the 2016 attack.
Exactly, popping up 6 years after the original Industroyer, 5 years after Trisis. And as the report points out, maybe a bit counterintuitively, Industroyer 2 is actually simpler than the original.
Simpler? How does that work? Usually sequels try to be bigger and badder.
Right. But here's the thing. The original Industroyer was that flexible framework with 4 different protocol modules needing C2 to deliver configured payloads. Industroyer 2, at least the version that was analyzed, uses only one of those protocol modules, specifically IEC 104.
Just one.
Just one. And it's packaged into a single executable file. And here's the kicker. Its configuration, like the IP addresses of the devices it's supposed to talk to, and the specific malicious commands it should send, that's all hard-coded right into the executable itself.
Hard-coded, so no dynamic instructions from C2.
Exactly. The report highlights this.
Yeah.
Industroyer 2 doesn't use C2 for its attack execution. Like Stuxnet in its attack phase. If Industroyer 2 gets dropped into an environment that matches its hard-coded configuration, it can just run autonomously and do its job.
Which makes it easier to deploy, maybe, if you know exactly what you're hitting.
Precisely. It strongly suggests the attackers did heavy reconnaissance beforehand to figure out the target environment well enough to bake the right configuration right into the malware. It's less of a flexible toolkit and more of a prepackaged automated weapon designed for a very specific scenario.
So a refinement, as the report calls it.
Yeah, the report views it that way, taking the knowledge gained perhaps from earlier Industroyer deployments or separate spying and distilling it down into a very efficient fire-and-forget kind of threat. And they also speculate, look, if they made an IEC 104 standalone variant, maybe they also made variants for the other original protocols, IEC 101, 61850, OPCDA. We just haven't seen them yet.
Interesting. Simpler code, but potentially very effective if the upfront intelligence is accurate and it avoids detection based on C2 traffic. Now, you said there were 2 threats found in April 2022.
Correct. Alongside Industroyer 2, researchers identified Incontroller, also known as Pipe Dream by some security firms like Dragos.
And Incontroller is.
The report presents this as a brand new framework, and the consensus among researchers cited is that it's potentially even more capable, more flexible, and more dangerous than anything seen before.
More advanced than Industroyer and Trisis. How?
It seems to combine capabilities seen in previous attacks into one package. The report describes it as a sort of Swiss Army knife for OT attacks. It has modules for reconnaissance mapping out industrial networks. It has modules for setting up backdoors and remote access, so C2.
Okay.
And it includes modules for directly manipulating specific models of industrial controllers, plus modules for directly manipulating a range of industrial protocols.
Wow, so it can target specific hardware and speak multiple languages?
Exactly. The report lists some of the protocols it supports, widespread standards like OPC-UA and Modbus, also FINS, which is commented on PLCs, and Codesys, which is a very widely used development environment for PLCs across many vendors.
That sounds like it could target a huge variety of systems.
That's the concern. This broad support gives it potential reach across many industrial sectors, well beyond just the electric grid. Think manufacturing, oil and gas, specifically LNG was mentioned as a likely target by Dragos, water systems, building automation. The list goes on. It also targets specific PLC models directly.
So, huge potential scope. Has Incontroller actually been used to cause physical damage in the wild yet?
Here's the good news, relatively speaking. As of when the Honeywell report was published, thankfully no. Incontroller hadn't been publicly tied to a successful real-world attack that caused physical effects.
So it was caught beforehand?
It appears so. It was identified and analyzed by security researchers before a confirmed destructive deployment, which is obviously a huge win for defenders, gives everyone a critical heads up.
That is good news. But the potential danger is clearly recognized.
Oh, absolutely. The report cites analysis calling Incontroller an exceptionally rare and dangerous cyber attack capability. Why? Because its flexibility could enable all sorts of attack scenarios, shutting things down, sure, but also subtle manipulation for sabotage. And alarmingly, the potential to incorporate logic to disable safety controllers, like Trisis did, but potentially across a much wider range of systems because of its diverse protocol and device support.
Okay, that's the 6. Stuxnet, BlackEnergy, Industroyer, Trisis, Industroyer 2, and Incontroller. Each one seems to represent a different step or capability. The Honeywell report says looking at them together reveals some important trends. Let's dig into those. What's the first big takeaway?
Right. The report pulls out several key trends from studying these 6 incidents together. Even with a small sample size, the patterns are pretty clear and, frankly, concerning.
What's trend number 1?
The first trend they highlight is this dynamic between modularity versus weaponization.
Modularity versus weaponization. Okay.
And they use the attacks against Ukraine's energy sector, BlackEnergy, Industroyer, Industroyer 2, as a perfect case study for this. Because the target was consistent and there are technical links, particularly between the Industroyer variants, it strongly suggests, a single adversary or group refining their approach over time.
So how does that sequence show this modularity weaponization trend?
You can see a clear progression. BlackEnergy in 2015 was kind of like phase 1. figure out how to cause disruption, using the tools available, misusing HMIs, coordinating actions, basically developing the initial strategy.
Right, learn how to attack.
Then, Industroyer in 2016 is phase 2. Build a more sophisticated, flexible, modular toolkit. This framework could gather info, deliver tailored payloads using specific protocols, but it still needed that C2 connection. It was powerful but complex.
Build the workshop.
Yeah.
And Industroyer 2 in 2022.
That's phase 3, weaponization. Take components or knowledge from the modular framework and create simplified, automated, prepackaged threats. Industroyer 2, using only IEC 104 and being autonomous if configured right, is exactly that. It's like taking the general-purpose tools from the workshop, making a specialized, efficient weapon for a known target.
I see. Build the flexible system, then spin off simpler targeted versions.
Exactly. The big insight is that investing in modular frameworks pays off later by enabling the creation of these easier-to-deploy, potentially harder-to-detect, weaponized variants.
That makes a lot of sense. Okay, what's the second trend the report identifies?
The second trend focuses on cyber-physical threats and industrial attack vectors. Basically, no matter how fancy the final payload is, Stuxnet, Incontroller, whatever, it doesn't matter if you can't get it onto the target OT network in the first place.
Right, you need to breach the perimeter somehow.
Every single one of these 6 attacks required that initial penetration into the industrial environment. The report looks at the common ways attackers actually achieve this.
And what are the main doorways they're using?
Based on threat data, the report points to 3 primary vectors consistently used to get into OT networks. First, network communications.
How does it usually work?
Often, attackers first compromise the business network, the IT side, which is usually less locked down. Then they look for connections or pivot points to move laterally into the OT network, maybe hitting engineering workstations or historian servers first. Once inside OT, they try to establish remote access or C2 for later stages.
Okay, so pivot from IT to OT. What's the second vector?
Removable media. Think USB drive.
Stuxnet's favorite, right? Still a big deal.
Oh, absolutely. The report emphasizes this, citing data from Honeywell's own USB threat reports over several years. Stuxnet showed how effective USBs are for bypassing network security, especially for getting into air-gapped or isolated OT segments.
And the report says all 6 of these threats could use USBs.
Yep, all are capable of leveraging that vector. And the data mentioned from recent years, like 2019 to 2023, is striking. Roughly half of all malware found on USB sticks plugged into industrial systems was specifically designed to spread via USB or use USB functions.
Half. Wow. So attackers know this works and are actively building tools for it.
They definitely know it works. And it connects to C2 as well. The report notes a big jump in USB-borne malware that also has C2 capabilities calling home for instructions, sending data out. That went from 44% in 2019 up to 72% in 2023.
So the USB isn't just dropping a payload, it might be dropping something that tries to establish a command channel.
Exactly. Which is relevant because, as we saw, frameworks like the original Industroyer, Trisis, and Incontroller often rely on C2. And here's a key finding. The report states that malware indicators actually associated with Stuxnet, BlackEnergy, Industroyer, Industroyer 2, and Trisis have been detected and blocked on removable media in real industrial sites since 2019.
So this isn't just theoretical. These specific threat actors or campaigns are still actively using USBs as a delivery mechanism.
The evidence strongly suggests it's an active vector for payloads related to these campaigns. They do note Incontroller indicators weren't available for that specific analysis timeframe. It just hammers home how critical managing removable media is in OT.
It really does. Okay, network, removable media. What's the third main attack vector?
The third one is the supply chain. And this one is particularly tricky.
Also.
Because the compromise happens before the hardware or software even gets to your facility. Hardware could be tampered with during manufacturing or shipping, to include hidden backdoors. Software could be infected with malware before it's installed. The report even mentions things like malicious USB hardware, maybe disguised as a keyboard or mouse, being introduced this way, referencing another Honeywell report.
That sounds incredibly hard to defend against.
It's a huge challenge. So those are the 3 main doors. Network, removable media, supply chain. Attackers use these to get inside the OT environment where they can then deploy things like the cyber-physical 6 payloads.
Okay, so we have modularity versus weaponization and the persistent attack vectors. What's the third major trend?
The third trend is about expanding capabilities. The basic idea is that each new successful attack adds to the overall knowledge base and toolkit of adversaries. They learn how to target new types of devices or new categories of systems like SIS with Trisis, Often this involves figuring out how to speak and manipulate new industrial protocols.
So each attack effectively increases the total potential attack surface.
Exactly. The net capability of the global cyber-physical threat landscape grows. And with these flexible modular frameworks, attackers can potentially mix and match capabilities demonstrated in earlier attacks to create new combinations.
You mentioned protocols. What are the key ones the report flags as being targeted by these six?
Yeah, the report specifically lists the protocols known to be supported or manipulated by the cyber-physical six. It's quite a list. Profibus, Stuxnet, Modbus, OPC-UA, OPC-DA, Industroyer, Incontroller, IEC 608705104, IEC 61850, IEC 608705101, all Industroyer family, FINS, and COBIS is both Incontroller.
That covers a lot of different systems and industries.
It really does. The report points out how widespread some of these are. OPC is a global standard. Modbus and Profibus are used in something like 18% of industrial networks. So by developing tools to manipulate these common languages, attackers gain potential access to a huge percentage of industrial operations worldwide, well beyond just energy.
So the toolkit grows by learning more languages. Got it. What's the fourth and final trend?
The fourth trend looks at the frequency of new cyber-physical attack capabilities. And the suggestion is that the time between the discovery of new, distinct threats in this category might be getting shorter.
Let's see, Stuxnet 2010, BlackEnergy 2015, that's 5 years. Then Industroyer 2016, Trisis 2017, that's basically annual. Then a gap. And Industroyer 2 and Incontroller both surface around April 2022, nearly 5 years after Trisis. It seems a bit uneven.
It is uneven, but look at the progression of capability. Stuxnet was 0 to 1. BlackEnergy showed a different approach. Industroyer brought frameworks. Trisis hit safety. Industroyer 2 weaponized the framework. Incontroller created a multi-tool. With each step, there's more public research, more code, more concepts for the next attacker to build on.
They don't have to reinvent the wheel every time.
Exactly. They're standing on the shoulders of, well, previous attackers and researchers. The report uses a really neat anecdote to illustrate this. Comparing Black Hat security conferences.
Oh, yeah.
In 2010, the year Stuxnet was found, apparently there was only one talk on industrial security, and the whole idea of cyber-physical attacks causing real damage was kind of laughed off by some as just fear-mongering, FUD.
Okay. Times have changed.
Dramatically. Fast forward to Black Hat 2022, the year Industroyer 2 and Incontroller came out. There was an entire track dedicated to cyber-physical security, and the keynote speaker reflected specifically on Stuxnet and how critical the situation had become. That's a massive shift in perception, driven by the reality of these 6 attacks.
That really paints a picture. So, given they're building on past work, does the report predict things will speed up?
It poses the question. With this accelerating knowledge base and existing frameworks to leverage, the report speculates that we might see new, distinct capabilities emerge faster than that initial 5-year Stuxnet to BlackEnergy gap. Maybe the intervals could shrink to, say, 3 or 4 years as adversaries get better at refining existing platforms or building new ones.
Okay, so the trends are increasing modularity leading to faster weaponization, persistent use of key vectors like USBs, expanding capabilities hitting more protocols and systems, and potentially an accelerating pace of new threat development. It's a lot. So let's pivot to defense. What does the Honeywell report say are the crucial takeaways for actually protecting against these kinds of attacks?
Right. The report offers very specific guidance grounded in how these 6 attacks actually worked. And the absolute foundation for almost all the guidance is this core observation. Every single one of these attacks required the attackers to have extensive, detailed intelligence about their specific target environment.
They needed blueprints, basically. What kind of PLCs, how the network's laid out, how the process actually runs.
Exactly that. Asset inventories, network diagrams, the actual control logic running on the PLCs and controllers, how the safety systems are set up, backup procedures, all the nitty-gritty details. You can't build something like Stuxnet or write custom SIS logic like Trisis, or even properly configure Industroyer 2 without knowing exactly what you're aiming at.
So attackers either need to do a ton of spying before the attack.
Right, reconnaissance.
Or they need a way to get inside the OT network first and then gather all that info.
Correct. The report says it requires one or the other, either deep pre-attack intel or successfully establishing persistence inside the network with a reliable C2 channel after the initial breach. That C2 connection lets them explore, map the network, maybe steal configuration files or backups to learn how things work.
And establishing C2 usually means getting through the network defenses.
Typically, yes. It often requires network penetration and installing some kind of backdoor. But this whole requirement for intelligence, that's a key defensive opportunity.
So if they need intel, step one is make it hard for them to get that intel.
Precisely. That leads to the report's first guidance point. Protect the information that attackers require. This isn't just about standard business data. It's about safeguarding sensitive details about your OT setup. Things like those asset lists, network drawings, the actual control logic code, backups, maintenance logs, even purchasing records showing what specific hardware you use. Anything that helps an attacker build that map needs to be locked down.
Don't hand them the keys to the kingdom or even the map to find it. Makes sense. What's guidance point 2?
Point 2 is implement strong security controls on beachhead systems.
Beachhead systems, what are those?
The report defines them as the likely initial landing spots for an attacker inside the process control network. These could be the systems they pivot to from the IT network, like an engineering workstation, or maybe a machine with an easily accessible USB port where malware could be introduced.
The first foothold inside the fort.
Exactly. So the advice is to really harden those specific systems. Use application whitelisting, strong endpoint security, multi-factor authentication, least privilege. Make it really tough for attackers to gain control of those initial entry points and use them to move deeper into the critical control segments.
Okay, secure the likely landing zones. What about controlling movement between zones? Network traffic.
That's guidance point 3. Implement tight security controls on all network traffic, but pay particular attention to outbound network traffic. Controlling network flow is basic hygiene, but the report stresses the importance of outbound controls in this context.
Why outbound specifically?
Because many of these advanced threats, especially those needing C2, rely on calling out to the attacker's servers. If malware slips in via USB or supply chain, strong outbound controls can block it from establishing that C2 connection needed to get instructions, send back stolen data, or coordinate the next phase. Cutting off C2 can effectively neuter certain attack stages.
Stop them from phoning home.
Got it.
Now, you mentioned earlier a shift in how newer attacks work, moving beyond just exploiting bugs. How does that affect defense?
Yeah, this is a really critical insight from the report, and it leads to some nuanced advice. The observation is that the newer threats, like Industroyer 2 and Incontroller, often don't need to find a traditional software bug or an unpatched system.
Really?
Instead, they work by abusing the intended functionality of the control systems themselves. They manipulate standard industrial protocols in malicious ways, or they overwrite legitimate controller logic with malicious logic.
So they're exploiting the design, not necessarily a flaw in the code.
That's the idea. The report points out that the target devices could be fully patched, functioning exactly as designed, but still be vulnerable, because the attacker can misuse their inherent control capabilities. The vulnerability isn't just a bug, it's the potential for the system's legitimate functions to be turned against it.
That really changes the game for defense, doesn't it, if patching isn't enough?
It absolutely does, which leads straight into the fourth guidance point. Prioritize vulnerability scanning and patching efforts where they are most effective, understanding this context.
So not all patching is created equal.
Pretty much. Given that lower-level controllers might be vulnerable even when patched, the report advises a pragmatic approach. Put higher priority on patching general-purpose computers, servers, engineering workstations of the systems, typically at the higher levels of the industrial network model, closer to IT.
Why those first?
Because they're often easier to patch, run more standard software, and are frequently the initial targets attackers compromise to get into the OT environment. Patching these robustly helps block those initial entry points.
And lower priority for the PLCs and controllers themselves.
The report suggests lower priority for patching the actual controllers, PLCs, SIS devices, down at the process control level. These are often much harder to patch, require extensive testing, and crucially, might still be vulnerable to misuse even as patched against known bugs.
So don't hold up critical patches on servers waiting for a risky controller patch.
Exactly. It's about resource allocation and risk management. Focus patching, where it gives the biggest security uplift against the most likely initial vectors, recognizing that for the lowest level devices, other defenses might be more critical than just chasing software patches.
Okay, if patching isn't the primary defense for those controllers vulnerable to misuse, what is?
That brings us to guidance point 5. Assume that all industrial control assets are vulnerable in the sense that their intended functions could be misused. Since you assume they can be manipulated, the next step is to monitor the process itself.
Monitor the physical process, like watch the actual machinery.
Yes. Use sensors and data you already have about the physical process, valve positions, motor speeds, temperatures, pressures, and look for anomalies. Compare what the process is actually doing against what it should be doing based on the control commands.
So if the system says a valve is closed, but physically it's open, or if pressure spikes unexpectedly,
that could be your first sign that a cyber-physical attack is in progress. Maybe manipulating sensors or sending rogue commands, even if your traditional cybersecurity tools haven't raised an alarm yet. Use the physical world as another layer of security sensors.
That's a fascinating approach, using the physics to detect the cyber attack. Okay, we talked about frameworks like Incontroller using lots of different protocols. How does that wide protocol support influence defense?
It broadens the threat landscape significantly. It means organizations outside the traditional targets like power grids manufacturing, oil and gas, buildings need to be increasingly vigilant if they use protocols like OPC-UA, Modbus, codices, FINs.
So guidance point 6 must be related to that.
Spot on. Point 6 is, if using any of the currently targeted industrial protocols, ensure that all associated networks are segmented and protected. If your operations rely on these protocols, the IEC standards, OPC, Modbus, Profibus, FINS, codices, make sure the network segments where they run are properly isolated using firewalls and strict access controls. Limit who and what can talk using those protocols.
Network segmentation is key. Can you secure the protocols themselves?
Yes, where possible, the report adds. Where available, like with OPC-UA, enable all available security functions including encryption, authentication, and access control. Some modern protocols have security baked in. If yours does, use those features. Don't just rely on the network perimeter. Secure the communication within the segment too.
Authenticate who's talking, encrypt the conversation. Good advice. What about the system's ability to handle bad commands if they do get through?
That's point 7. Consider the potential risks of malicious or unintended control commands and design your control system with resiliency. Since these attacks work by sending bad commands or changing logic, you need to design the system anticipating that possibility.
Oh.
Build in redundancies, fail-safe mechanisms, checks and balances in the physical process itself, so that even if a malicious command is received, its impact is limited, or the system can transition to a safe state automatically. It's about making the system inherently robust against misuse.
Designing for failure, basically, but assuming the failure might be malicious.
A good way to think about it. It blends safety engineering with cybersecurity awareness. And finally, circling back to Trisis and the safety system threat.
Right, that was deeply worrying.
So the 8th and final guidance point is emphatic. Secure SIS equipment. Given that safety systems are a proven target, you must ensure they are adequately segmented, isolated in their own distinct security zones, separate from the main process control network. And apply adequate controls on all SIS-related data flows. Strictly control who or what can communicate with the SIS, modify its logic, or even read its status. Protect the protector.
Okay, so a layered approach. Protect intel, secure entry points, control traffic, especially outbound, prioritize patching smartly, monitor the physical process, segment based on protocols and secure them, build resilience, and heavily protect safety systems. That's a solid defensive posture based on these attacks. Looking ahead now, what does the report suggest we should expect next in this space?
The report uses Incontroller, the latest and arguably most advanced framework, as a potential indicator of future directions.
A blueprint for what's coming.
Potentially, yes.
Yeah.
Remember the modularity versus weaponization trend?
Yes.
Just like Industroyer led to the simpler Industroyer 2. The report anticipates we'll see a similar evolution from Incontroller's flexible toolkit. Adversaries could use its components to launch complex multi-stage campaigns, or they could spin off simpler, targeted attack packages derived from specific Incontroller modules, maybe focusing on just one protocol or controller type.
So, more specialized weapons born from the flexible framework.
That's the prediction. Continued refinement of these modular platforms, and then weaponizing specific pieces for easier deployment. And there's another angle. If attackers do successfully use Incontroller in the wild,
yes,
its built-in reconnaissance features, using protocols like OPC-UA or DNP3 to map out victim networks, could provide them with incredibly detailed intelligence.
Which they could then use to build.
Even more precisely targeted, packaged threats designed specifically to disrupt, manipulate, or destroy the systems they just mapped out. It feeds back into itself.
Wow, a dangerous feedback loop. Use the tool to learn, use the learning to make better weapons.
Exactly. The report also projects some expanding reach. We talked about the protocols. While maybe chosen initially for energy sector targets, they're used everywhere.
So attacks using these existing tools will likely spread to other industries.
The report expects that, yes, attacks on manufacturing, oil and gas, etc., using the existing frameworks. But it also predicts adversaries will go further. They'll likely extend these frameworks or build new ones to support entirely new industrial protocols and attack entirely new types of systems.
Expanding the attack surface even further.
Correct. Targeting industries or systems that maybe haven't been hit by one of the original 6, but use different communication standards. The threat keeps broadening.
So it really paints a picture of a threat that's not just sitting still. It's actively growing, technically better, more efficient to deploy, and aiming at a wider and wider range of targets.
Compounding, as the report puts it, building on itself.
Okay, so let's try to wrap this deep dive up. What's the final word from the Honeywell report on the cyber-physical 6 and what they mean?
The conclusion is pretty stark. Cyber-physical attacks are real. They work. They cause significant physical impact. And they represent a serious growing threat to industry and critical infrastructure globally.
And the history shows they're evolving.
Clearly. The path from Stuxnet to Incontroller shows a definite evolution in capability, scope, and potentially speed. Any future security planning has to factor in not just today's threats, but where this trajectory seems to be heading.
It sounds challenging, maybe even a bit overwhelming. Is there any good news in the report's conclusion?
There is, actually. The report is clear. While the threat is serious, it's not unstoppable. Mitigation is possible.
How so? Where are the opportunities for defenders?
Well, remember that critical need for attackers to gather detailed intelligence. That's a major opportunity. If you protect that information well, make reconnaissance hard.
You slow them down or stop them early.
Right. Strong basic IT security helps prevent the initial breaches often used for that recon.
Right.
Proper OT network segmentation, robust controls on all those attack vectors network, USB, supply chain, makes it much harder for them to get initial access in the first place.
And even if they get access.
Understanding how these attacks work, like manipulating protocols or logic, helps you focus defenses. Building that system resilience minimizes the physical damage if an attack does get through. Monitoring the limited entry points into OT offers chances for early detection. The need for C2 in many cases provides specific traffic patterns to look for.
So the attacker's own methods and requirements create defensive openings.
Exactly. The shift from focusing only on bugs to understanding protocol manipulation highlights why segmentation and protocol-level security, like in OPC-UA, are so vital now. The increasing power of frameworks means you need defenses at multiple layers. Block the intrusion, detect the framework, stop the C2, build resilience. And the expanding reach means security needs to keep adapting to cover new protocols and techniques.
It's a dynamic battlefield, but understanding the enemy, based on these 6 crucial examples, gives us a strategy. Protect the intel, lock down the vectors, monitor everything, including the physical side, and build systems that can take a punch.
That sums it up well. A defense-in-depth strategy informed by the hard lessons learned from the cyber-physical 6.
It's clear these threats are very real and evolving fast. Anyone involved with industrial systems or critical infrastructure really needs to internalize these lessons.
It's moved way beyond a niche IT security issue. It's about operational reliability and public safety now.
So as we close out this deep dive, here's something to think about. We've seen the pace potentially quickening, the capabilities broadening, the targets diversifying. Consider the essential systems underpinning your own daily life: power, water, transport, manufacturing. How might this evolving cyber-physical threat landscape, this trend towards more capable and widespread attacks, affect those systems and ultimately you in the coming years?
It's a question that really underscores why understanding and addressing OT cybersecurity is becoming so fundamentally important for all of us.